Ali Shahin Shamsabadi is from University of Lille, not too far, and he's going to speak about differential private speaker anonymization. Ali.
Hello everyone, good morning. Yeah, I'm Ali Shahin Shamsabadi, and currently I'm at the Alan Turing Institute, but this is the work that I've done while I was at INRIA, Vector Institute, and Alan Turing Institute, and last week I joined Brave. Sharing real-world speech utterances is the key to the training and deployment of the voice-based services, such as voice-based dictation, voice-based assistance, or voice search that we all use in our daily lives. When we use this application in our daily life, our speech is collected by the service provider to either perform our queries or to train their models, for example, speech recognition models, on our data, on our speeches that are real, diverse, and annotated by the human, because they want to achieve the state-of-the-art performance. So you might be wondering that why this guy is talking about speech in a privacy conference. So well, speech contains linguistic content, such as what is being said, prosodic content, such as the stress, rhythms, intonation when you are talking, and speaker information, who is saying it. Therefore, speech is a very sensitive data, and it can be considered as a biometric modality that can identify the speakers of the speech, right? For example, if a malicious party has access to our speech utterances, they can impersonate us to break to our systems or houses, or they can assemble fake recording that we never said before. So I hope that I convince you that when you want to share your speech, you should be careful about the privacy and security risk that you might face later on. Inspired by the voice privacy challenge in this work, we consider a scenario where we produce a speech as the customers of the company or whatever, and we want to share this speech with the service provider, either to use their services or help them to train their models. But as we saw before, a speech contains or leaks identifying information that is embedded in the speaker's voice. So the goal here is that can we design a speaker anonymization techniques that hide the speaker's information but preserves all the linguistic and prosodic content that we saw before? This is the main goal. Okay, you might be thinking that let's do the cryptography, but here, a speaker anonymization cannot be done using the cryptographic solution because they provide confidentiality, not the privacy. For example, if you use a cryptographic solution, it makes the human annotation of the speech impossible, so we cannot listen to the speech and annotate and transcribe it. Another naive approach is that why not just going from the speech to the text and then going back from the text to the speech. In this way, you can remove all the speaker information clearly, right? But as you can imagine, it will destroy significantly the utility of your speech, especially the linguistic and prosodic content that we want to preserve. And the main issue here is that you will lose the diversity of the speech when you do this. To address these challenges recently, the state-of-the-art speaker anonymization technique said that, okay, let's separate speaker information from all the other information, which is linguistic and prosodic content. And they generate the speech only by removing the speaker information. So basically, what they do is that they rely on three features. One of them is the pitch, a sequence of the pitch that represent the prosodic content. The other one is the BN, bottleneck features, that conveys the fine-grained linguistic content of the speech. And the last one is the speaker embedding, which is usually the intermediate layer of the neural network that is trained to identify the speaker. And the bottleneck feature here is the intermediate layer of the speech recognition model, the model that is trained to transcribe your speech to the text. And then when you have these three features, you can use the pitch and BN features of your original speech because you think that they don't have any speaker information. But now you can replace the speaker information, which is the X vector here, with the X vector of the public speaker that you choose randomly and independently of your original speech to not contain any information about your original speech. You might think that, okay, are we done with the speech anonymization? But unfortunately, the answer is no. In this work, we demonstrate that this disentanglement of the speaker information is not perfect, which means that linguistic and prosodic contents still contain residual speaker information. So basically what we do, we mount an attack by training the speaker identification model directly on these two features, BN feature and pitch. And we surprisingly see that we can predict the identity of more than 900 speakers with the accuracy of 97%. So it clearly shows that these features are predictive of the identity of the speaker. So what can we do? In this work, we use the idea of the differential privacy that I'm sure in this week you saw a lot, this definition. So I wouldn't spend much time on this, just to let you know that in our setting, X is the speech utrans, A is the anonymization technique that produced the anonymized speech utrances, and of course, epsilon is the privacy budget. We use the local differential privacy, and when we enforce DP, here it means that we make any two utrances indistinguishable to some extent. That is formulated based on the epsilon, the privacy budget. Which means that we can bound the risk that an adversary who is looking at the output of the anonymization technique, which is anonymized speech utrances, to predict the identity of the speaker. So you might think that, okay, we can easily enforce DP by adding directly noise to these features, right? The BN features and pitch. But again, we show that this significantly destroys the utility of the speech because you don't preserve the linguistic and the pitch that prosodic contents that we want. So what we do, we carefully design a machine learning based feature extractor, differentially private feature extractor here, that preserves the desired information, and it adds necessary noise to these features using the noise layer at the, like somewhere in the network to guarantee the differential privacy. Let's first look at the DP pitch extractor, which is mainly a fully convolutional autoencoder that is located on top of the traditional pitch estimator. And the way that we train it is as follows. We consider a public data set that is disjoint from your private data set. And let's say X is the speech utrans of K frame. Frame is just a small portion of your speech, such as every 10 milliseconds, for example. Then we compute the pitch, one-dimensional pitch value for each frame. And then we have the encoder that compute the latent representation of the pitch. And now here we have a noise layer that adds Laplace noise, which is a scale based on the sensitivity of the encoder. And thanks to the sigmoid here, we can easily compute the sensitivity. It's just basically the dimension of the output of the encoder. And then we have the decoder that receives this perturb pitch and output the perturb pitch, latent representation to the pitch. And then we have the loss function here that maximize the correlation between the original pitch that we have here and the DP pitch that we have here. This helps us to preserve the global dynamic of the pitch, which is basically the prosodic content of the pitch that we want to look. And here I show you the empirical privacy versus analytical privacy. You can see the clear relationships between the empirical privacy protection and analytical privacy. And you can see that as we make the epsilon smaller and smaller, we can significantly improve the empirical privacy protection, for example, from 62 to somewhere 95. And for the DPBN, we do the same idea. We have the noise layer, but here is in the speech recognition model. Because of the interest of the time, I wouldn't go to the details of that. I just want to show here that our DP-BN features can be shared with the service provider with very negligible effect on the accuracy here, but with the huge improvement in the privacy from here to somewhere close to 100. And at the end, we plug all of this to the speaker anonymization pipeline. And thanks to the post-processing and composition property of the DP, the whole pipeline now is DP. So here I would like to play a sound for you to have the idea that how they sound. This is the original one.
Number 10, fresh Nelly is waiting on you. Good night, husband.
And this is the one without any DP.
Number 10, fresh Nelly is waiting on you. Good night, husband. Number 10.
And this is with, for example, epsilon 10.
Good night, husband.
Number 10.
And here is another voice. At the
early.
end, I just want to show you that three main messages. One of them is that in the yellow column, you can see that we add provable privacy guarantees to the speaker anonymization. In the green column, you can see that we improve the empirical privacy protection significantly, almost by double. And in the last column, you see that accuracy, we didn't drop the accuracy much. Thank you so much.
Thank you, Ali. Fascinating. Any questions in the room? All right. Thurston is asking, I didn't fully understand, in order to achieve DP, the mechanisms has to be able to generate an arbitrary element from the complete universe, not only the database at hand. How does this algorithm generate arbitrary utterances at potential chaff?
Sorry, could you repeat it?
How does... Why am I doing this?
I have no clue. So, hi, good morning. Very interesting talk. Thanks a lot. I was wondering, so in order to achieve DP, the mechanism that achieves DP has to be able to generate arbitrary elements from the entire universe, right? So it's not sufficient to only sample elements from the database, but you need to know the entire universe. And if I understand correctly, then your universe is all potential utterances. And now I was wondering how you can generate arbitrary utterances, because that would be required, I guess.
So the way that we do that, we use the Laplace mechanism to make the speaker anonymization DP. So for the Laplace mechanism, we just add the noise layer on top of the encoder, for example here, that add the noise to each element of the pitch value that we have. New, perfect.
I think we'll park it there, guys. Maybe for the offline discussion. I've got another question for you, Ali, while Jeremy's setting up. Why not use metric LDP, a relaxed notion allowing output indistinguishability to be scaled by the respective inputs? As such, the semantics of input pairs can be preserved.
So here, to preserve the semantic, we first split the features, for example, to speaker information and non-speaker information. And there we apply the DP because we know that which feature is conveying which message. And then we go back to the speech utterances with the hope that, okay, we preserve the semantic. And now, I mean, we designed the loss function in the feature space rather than a speech space to be easier to train.
Thanks, Ali. Let's thank Ali again.